Hello students, welcome to EPG Pathshala. I am Dr. Manjula Sharma from University of Delhi. Today we are going to talk on the module Analog Ammeters and Voltmeters Part 2 under the paper Measurements and Instrumentation. After completing this module, the students will be able to understand about the following topics. First, the ammeter shunts. We will also study the construction of shunts, then the arrangement for temperature effect correction. Next would be the multi-range ammeters and the multi-range ammeters with universal shunt. Next, the voltmeter multipliers. We will also study the construction of multipliers. Towards the end, we will study about the multi-range DC voltmeters. We will also study in detail the individual multipliers and potential divider arrangement. Students, the analog ammeters and voltmeters are classed together as there are no fundamental differences in their operating principles. The action of all ammeters and voltmeters, with the exception of electrostatic type of instruments, depends upon a deflecting torque produced by an electric current. In an ammeter, this torque is produced by current to be measured or by a definite fraction of it. In a voltmeter, this torque is produced by a current which is proportional to the voltage to be measured. Thus, all voltmeters and ammeters are essentially current measuring devices. The essential requirements of measuring instruments are that its introduction into the circuit where measurements are to be made does not alter the circuit conditions. Second, the power consumed by them for their operation should be small. Students, now let us study about the ammeter shunts. The basic movement of a DC ammeter is a PMMC d'Arcenvois galvanometer. The coil winding of a basic movement is small and light and can carry very small currents, since the construction of an accurate instrument with a moving coil to carry currents greater than 100 mA is impracticable owing to the bulk and weight of the coil that would be required. When heavy currents are to be measured, the major part of the current is bypassed through a low resistance called a shunt. Figure 1 shows the basic movement or the meter and its shunt to produce an ammeter. The resistance of the shunt can be calculated using conventional circuit analysis. Looking at the figure 1 in the previous slide, let us define the various terms used. The Rm is the internal resistance of the movement, that is the coil. Im is equal to Ifs, which is equal to the full scale deflection current of the movement. Rsh is defined as the resistance of the shunt, Ish as the shunt current, and I is the current to be measured. Since the shunt resistance is in parallel with the meter movement, the voltage drops across shunt and movement must be the same, or Ish Rsh is equal to Im Rm. Thus, Rsh is equal to Im Rm divided by Ish. But Ish is equal to I minus Im. Therefore, Rsh, that is the resistance of the shunt, is equal to Im multiplied by Rm divided by I minus Im. Simplifying the above equations, we get I by Im is equal to 1 plus Rm by Rsh. This ratio of total current to the current in the movement is called multiplying power of shunt. Thus, the multiplying power M is equal to I by Im is equal to 1 plus Rm by Rsh. The resistance of the shunt Rsh is defined as Rm by M minus 1. Thus, the shunt resistance used with a d'Arsonval movement may consist of a coil of resistance wire within the case of the instrument, or it may be external shunt having a very low resistance. Students, now let us study the construction of the shunts. The general requirements for the shunts are: the temperature coefficient of shunt and instrument should be low and should be as nearly as possible the same. Second, the resistance of shunts should not vary with time. Third, they should carry the current without excessive temperature rise. Fourth, the shunts should have a low thermal electromotive force. Manganese is usually used for shunts of DC instruments as it gives low value of thermal EMF with copper, although it is liable to corrosion and is difficult to solder. Constantan is a useful material for AC circuits since its comparatively high thermal EMF being unidirectional and is ineffective on these circuits. The construction of shunts is the same as that of low resistance standards. Shunts for low currents are enclosed in the meter casing, but for currents above 200 amperes, they are mounted separately. Shunts for heavy currents are mounted externally. Figure 2 shows an external shunt. It consists of evenly spaced sheets of resistive material welded into large blocks of heavy copper on each end of sheets. The resistance material has a very low temperature coefficient and a low thermal electric effect between the resistance material and the copper. The current terminals on each end of the shunt carry the load current, while the binding posts or the potential terminals on each end of the shunt are used to connect the ammeter to the shunt and carry only the current which passes through the meter or the movement. Meters using external shunts are usually designed to operate at a full-scale voltage rating. These ratings are usually 50, 75 or 100 millivolt. This is the voltage across the potential terminals of the shunt when full-scale current flows through the load. In as much as the current produced in the meter deflection is a function of the voltage drop across the potential terminals of the shunt and the resistance of the instrument, including the leads. The meter used with external shunts must have leads with a specified resistance to accompany the meter. Leads supplied with the instrument should never be changed, and also no portion of the leads should be cut off, otherwise it will lead to serious calibration errors. Next we will study about the arrangement for temperature effect correction. The temperature error can be eliminated when the shunt and the moving coil are made of the same material and kept at the same temperature. This method, however, is not satisfactory in practice, as the temperatures of the two parts are not likely to change at the same rate. An additional disadvantage of using copper shunts is that they are likely to be bulky, as the resistivity of copper is small. Copper shunts are only occasionally used in instruments with built-in shunts. The arrangement normally used is shown in the figure 3, which shows the meter shunt and the swamp resistance. In this case, swamping resistance of manganese having a resistance 20 to 30 times the coil resistance is connected in series with the coil, and a shunt of manganese is connected across this combination. Since copper forms a small fraction of the series combination, the proportion in which the currents would divide between the meter and the shunt would not change appreciably with the change in temperature. Students, now we will consider the multi-range ammeters. The current range of a DC ammeter may be further extended by a number of shunts selected by a range switch. Such meter is called a multi-range ammeter. Figure 4 shows a schematic diagram of multi-range ammeter. The circuit has four shunts: RSH1, RSH2, RSH3 and RSH4, which can be put in parallel with the meter movement to give four different current ranges, that is I1, I2, I3 and I4. Low range ammeters use a multi-position make before break switch, as is shown in figure 4. The break switch provided on the case of the instrument. This type of switch is essential in order that the meter movement is not damaged when changing from the current range to another. If we provide an ordinary switch, the meter remains without a shunt, and as such it is unprotected when the range is changed. When larger currents are used, the connections are brought out to binding posts, and the loads are connected directly to the binding post, which is identified with the described current range. Multi-range ammeters are used for ranges from 1 to 50 amperes. When using a multi-range ammeter, first use the highest current range, then decrease the current range until good upscale reading is obtained. The universal shunt or add-on shunt is used for multi-range ammeters. The advantage of a universal shunt is that it eliminates the possibility of the meter being in the circuit without a shunt. But this advantage is gained at the cost of a higher meter resistance. Now, let us consider the universal shunt. The figure 5 shows the multi-range ammeter using universal shunt. The universal shunt is presented here in a different form. Consider that the meter ranges have to be extended to I1, I2 and I3. For the arrangement shown in figure 5, we have for switch at position 1, Im Rm is equal to I1 minus Im multiplied by R1. Therefore, M1 is equal to I1 by Im, which is equal to 1 plus Rm by R1, or R1 is equal to Rm by M1 minus 1. For switch at position 2, Im R1 minus R2 plus Rm is equal to I2 minus Im multiplied by R2, or the final expression for R2 is equal to R1 plus Rm divided by M2. For switch at position 3, Im multiplied by R1 minus R3 plus Rm is equal to I3 minus Im multiplied by R3, or R3 is equal to R1 plus Rm divided by M3. Thus, the values of different selections of resistances, that is R1 minus R2, R1 minus R3 and R3 may be found. Students, now let us study the voltmeter multipliers. A d'Arson valve basic meter movement is converted into a voltmeter by connecting a series resistance with it. This series resistance is known as a multiplier. The combination of the meter movement and the multiplier is put across the circuit whose voltage is to be measured. Figure 6 shows the meter with a multiplier. The multiplier limits the current through the meter so that it does not exceed the value for full scale deflection and thus prevents the movement from being damaged. The value of a multiplier required to extend the voltage range is calculated as follows. Let Im is equal to the full scale deflection current of meter. Rm is equal to the internal resistance of meter movement. Rs is the multiplier resistance. Small v, the voltage across the meter movement for current Im. Capital V is the full range voltage of instrument. For the circuit of figure 6 in the previous slide, small v is equal to Im Rm and capital V is equal to Im multiplied by Rm plus Rs. Therefore, Rs is equal to V minus Im Rm divided by Im. We can also express the result in terms of multiplying factor of multiplier. Multiplying factor for multiplier, that is M, is equal to capital V by small v, which is equal to 1 plus Rs by Rm. Thus, resistance of multiplier, that is Rs, is equal to M minus 1 multiplied by Rm. Hence, for the measurement of voltage M times the voltage range of the instrument, the series multiplying resistance should be M minus 1 times the meter resistance. Thus, to extend the voltage range to 10 times the instrument range, Rs should be equal to 9 Rm. Now, let us study the construction of multipliers. The essential requirements of multipliers are: first, their resistance should not change with time. Second, the change in their resistance with temperature should be small. Third, they should be non-inductively wound for AC meters. The resistance materials used for multipliers are manganese and constantan. Multipliers are mounted inside the instrument case for voltages up to 500 volt. For higher voltages, the multipliers may be mounted separately outside the case on a pair of binding posts to avoid excessive heating inside the case. Now, let us study the multi-range DC voltmeters. In a multi-range voltmeter, different full-scale voltage ranges may be obtained by the use of individual multiplier resistors or by a potential divider arrangement. First, individual multipliers. We can obtain different voltage ranges by connecting different values of multiplier resistors in series with the meter. The number of these resistors is equal to the number of ranges required. Figure 7 shows multiplier resistors Rs1, Rs2, Rs3 and Rs4, which can be connected in series with the meter by a range selector switch. Consider that the ranges desired are V1, V2, V3 and V4. Then the corresponding multiplier resistances can be obtained. Thus, we have Rs1 is equal to M1 minus 1 multiplied by Rm, Rs2 is equal to M2 minus M1 multiplied by Rm, Rs3 is equal to M3 minus 1 multiplied by Rm, and Rs4 is equal to M4 minus 1 multiplied by Rm. Now, the potential divider arrangement. Another multi-range voltmeter is shown in figure 8, in which the connections are made at the junctions of resistances R1, R2, R3 and R4 in series to obtain the voltage range V1, V2, V3 and V4. These connections are brought out to binding posts on the instrument, and the instrument is connected to the proper binding post for the desired voltage range. The series resistances for the voltage ranges V1, V2, V3 and V4 can be computed as follows, where R1 is equal to M1 minus 1 Rm, and similarly for R2, R3 and R4. This system has the advantage that all multipliers except the first have standard resistance values and can be obtained commercially in precision tolerances. The range multiplier R1 is the only special resistor which must be manufactured to meet specific circuit requirements. Multi-range voltmeters are very effective for moderate range voltages. For higher range voltages, it is often desirable to use external resistors in connection with a given voltmeter. In using a multi-range voltmeter, it is usual procedure first to connect the voltmeter to the highest voltage range terminal or set the switch to the highest voltage which the instrument will read. Then connect the instrument to the circuit and measure the voltage. Then decrease the ranges of the instrument until a good upscale reading is obtained on the voltmeter. So students, let us see what we have learned in this module. We learned about the ammeter shunts, the construction of the shunts, then the arrangement for temperature effect correction. We also learned about the multi-range ammeters and the multi-range ammeters with universal shunt. We read about the voltmeter multipliers and the construction of the multipliers. And towards the end, we studied about the multi-range DC voltmeters, in which we covered the individual multipliers and the potential divider arrangement.